Also, there is one very important fact which we missed, that is they just did PV indicator diagram, right? So I can draw a PV indicator diagram for isothermal as well as adiabatic, but what would be the difference in the slope of PV indicator diagram for isothermal and adiabatic? Let's figure it out. Okay, so I'll be omitting all those non-important things which you have already noted down. So this goes, and these points, these two are very essential points. You can mark them as notes or important points for the difference in isothermal and adiabatic process. Okay, right, this much space will do for us. Okay, let's start. See, PV indicator diagram is this, right? Suppose this side is P and this side is V. Okay, suppose this is P1 V1. The expansion and compression are two facts which can be done with a piston and a gas experiment. So if the gas is in expansion mode or gas is expanding, what will happen? Pressure is going to decrease or increase. Volume will increase and pressure will decrease, right? So point will be somewhere here and the graph should be this. But what would be the slope of this graph? Slope means how steep this graph could be. This graph could be this much steep or it could be this much slant. Okay, there are possibilities. So what we are going to do, we are going to study about how slopes or isothermal and adiabatic processes vary. Slope is given by rate of change of y-axis upon x-axis, which is dp upon dv. This is what we are going to do in both the things, both the equations. I'll start with this thing, PV is equal to constant. PV is equal to constant, differentiating both sides. Up now, both P and V are variables. So that is, right now we are doing a differentiation of two functions. That is first function into differentiation of second plus second function into differentiation of first, right? That's a power rule. So here it will be, product rule. So P times differentiation of second, that is dV, plus V times differentiation of first, that is dP. Differentiation of constant is 0. So I'll get, what I have to get is dP upon dV. So V dP is equal to minus P dV. This dV comes in the denominator side, I'll get dP upon dV. This is equal to minus P upon V. So this is the slope in case of isothermal. Let us compare it with the slope which we are going to figure out in adiabatic process. Here PV raised to power gamma is the constant. Okay, this is the equation. So PV raised to power gamma is a constant. Differentiating both sides, first function into differentiation of second. X raised to power n is what? N times x raised to power n minus 1. That's the formula of differentiation. So here it will become gamma times V raised to power gamma minus 1. This is the first function into differentiation of second into dV, right? Because V is still a variable, so we'll have to differentiate V again and I'll get V dV as we have done there. Plus V raised to power gamma times differentiation of first, that is dP. This is equal to 0. Now I want dP over dV. So taking this whole term this side, V raised to power gamma times dP is equal to minus P gamma V raised to power gamma minus 1, right? So this thing into what? This I have left dV. So this term goes there and this term comes here. I'll be getting dP over dV is equal to minus P gamma V raised to power gamma minus 1 over V raised to power gamma. What is V raised to power gamma minus 1? Or I can just bring this V raised to power gamma on the numerator side, it will become V raised to power minus gamma, right? So I'm doing it here only. This term goes on the numerator side, becomes V raised to power gamma, and these two terms implies V raised to power gamma minus 1 plus gamma, right? Because they are in multiplication. So this becomes plus gamma. So these two terms cancels out and I am left with minus 1. V raised to power minus 1, that means 1 upon V. Okay. So now I am left with 1 upon V. So this is the final formulation, that is minus gamma times, gamma I have written it just in front, minus gamma times P upon V, whereas in that case I had only minus P upon V. So gamma, the slope, the difference in slope actually depends on the value of gamma. See, gamma is the ratio of specific heat capacity of gas at constant pressure to that of at constant volume, Cp upon Cv. Since gamma is a quantity which is greater than 1, that means this slope is more. So the slope or the graph would be steeper in case of adiabatic as in isothermal case. So let me make two graphs for expansion and compression. Here I am representing expansion mode and compression. Okay, starting with this point, this is P1 V1. In case of isothermal, graph would be like that, but in adiabatic the graph would be more steeper, whereas in this case this is the trend what graphs are following in case of expansion, whereas in case of compression, starting from this point, the compression in case of isothermal would be this, sorry, with black, compression in isothermal would be in this, and adiabatic would be more steeper, and that would be this. So this is the difference in the slope of PV indicator diagram for isothermal process and adiabatic process.